In Lesson 2, we're going to learn about definite integrals. We've actually studied indefinite integrals already. Indefinite integrals are antiderivatives when you work backwards and you have to add the plus c. So in today's lesson, we get to forget about the plus c. We won't talk about antiderivatives a whole lot, but that will come into play in a couple days. So a definite integral is written this way. You can see it looks very familiar to some of the antiderivative stuff we did. The main difference is that we have a lower limit and an upper limit, and those are x values. And they basically tell us the x values that we're interested in, and we want to find the area under the curve between those two x values. So we've been talking about that with estimating over the last day or so. So we could really say that this notation means the following. Okay, I know this might look a little confusing yet, but basically what we're doing here is we're finding a y value, we're finding the overall change in x that has occurred from b to a if we make this number of rectangles, and so multiplying these together tells us the area of each individual rectangle, and the number up here is saying we're going to make infinitely many rectangles in between A and B. And so when we do that, we get overall the exact value of the area under the curve. And instead of having to write all of this every single time, we're just going to say this means the same thing. So you are welcome, because it does make life a lot easier. I know it might seem a little confusing right now, but that's really what it means. Find the exact area under the curve. And so in general, this means that all the area is going to be above the x-axis. It's going to be nice and positive. When area falls below the x-axis, we need to talk about what that will mean. And so that will come in a future example here. So we're going to try to find the area under the curve for the following ideas here. The first one is just the function 3. And we're going to look at it from in between the x values of 2 and 9. So if we were to draw an equation for that, or draw a graph of that, excuse me, we'd start with something like this. Y equals 3 just goes something like that. And we would be interested in what's going on between 2 and 9. So we're trying to find this area. It happens to be a nice rectangle. And our base of that rectangle is a length of 7. The height is 3 because it's a consistent y value there. And so in the end, this question would get us 21. This next one, we're going to look at the absolute value between absolute value of x between -2 and 1. So again, if we draw a picture, absolute value will look something like just that V shape there. Go all the way to -2 and then just a +1 right there. So you see we have two triangles. All these things today we'll be able to figure out through geometry. The triangle on the left side, we would have 1/2 times a base of 2 times a height of 2 for that triangle. And to that we're going to add a triangle that has a base of 1 and a height of 1. So if I go through and I simplify that a second, the first triangle would have an overall area of 2. The next one would have an area of 1/2. So overall our answer is 2.5. And our last one is it's the integral square root of 9 minus x squared between -3 and 3. So again, what's the area under the curve? This one's a little bit trickier. For this one, we just have to remember that if this whole inside piece we're calling y, so y equals that. Come on, there we go. Okay, if I were to square both sides, I get y squared equals 9 minus x squared. And if I bring that x squared to the other side, I get this. This is the equation of a circle that has a radius of 3. And so I know that might be a little confusing, or at least something we don't use a whole lot. But I do think it's important that we understand that sometimes we just have to think through the geometry and we can understand this a little bit better. So when it's written this way in the square root form, that means it's the top half of this particular circle that we're interested in. So the graph would look something like this. Starting all the way at -3 and going to +3. And so if the radius is 3, that means it also goes to a height of 3. And it would just look something like this. That's a bad circle there, but anyways, we're finding the area of that. And so for this one, we'd have to take half of the area formula, so 1/2 times pi r squared, so pi times 3 squared in this case. And that just gets us 9 pi over 2, and it is perfectly fine if you leave your answer in that form. So if area, or if the function goes below the x-axis, all you need to do is count the area as negative, and that may seem kind of funny or seem kind of weird, but that's basically all there is to it. So for a function where part of it is above and part of it's below, you actually need to do this twice. And let's just look at a very quick example of that. If we were to graph the function 3 minus x, I know you guys remember all of this from maybe freshman algebra. Okay, but we would have a y-intercept of 3, a slope of -1, so just kind of go down like that. And we're interested in the part of the graph, it looks like from 4 to 8. So at 4, if I plug a 4 in for x right there, I'm going to get a negative y value. It's going to be a y value of -1. And if I think about this, when I plug a 3 in there, that's where I find this x-intercept right here. So that's at 3. That must mean 4 is somewhere around here. And if I go all the way to 8, let me extend this a little bit. We'll say 8's right about there. I need to think about this part right here. So in general, if you think through the picture of it, this right here has a length of 1. If I plug an 8 in there into the overall function, I get -5. So the overall distance covered here is 5. And my overall length right there would be a length of 4. So I have a trapezoid here. 2 parallel sides, a difference between them of 4. So hopefully from sections 1 and 5, we're somewhat familiar with the fact that area of a trapezoid is 1/2 times the sum of your 2 bases times the height. We just need to remember that this has been flipped on its side a little bit. So in this case, I would have 1/2 times 1 plus 5 times a height of 4. Go through and I simplify that. I get 1/2 times 6 times 4, which is 12. So that is kind of the area between the curve and the x-axis. We think of area as positive, but when I need to think of this notation right there, because it's below the x-axis, that part would be -12 because it was underneath. So just to kind of make a connection here, that might be our answer for that. In general, if we're just talking about area, we'd say 12, but because it's in the context of an integral, we have to say -12. So let's look at a more complicated question like this. If we knew that the area between 0 and pi, so this upper limit here is pi, I know it's kind of hard to read, of the function sine, we can actually prove this in a little bit. If that area is 2, based on what we know about sine, what can we say about these following questions? So let's just do a very quick sketch and review of the sine function. It kind of goes like that. This right here is pi, and this is 2 pi. And what they're telling us is the area of this part of the curve right there is 2. So in part A, we're going, the limits are from pi to 2 pi. This is a pi right there. So if we kind of remember some things about symmetry, if this area is 2, the overall area there is also 2. But because it is underneath the x-axis, we have to say the answer for this is -2. For part B, the area under the curve from 0 to 2 pi, while those two parts offset, so that part, the area would be 0. For part C, It's from 0 to pi over 2. So if it's hard to read, this part, upper limit there is pi over 2. Again, we have some symmetry in this part. So we're looking at right in the middle. That must mean that if the overall area from 0 to pi is 2, from 0 to pi over 2, the area is 1. Part D says from negative pi to pi, so just remember for that negative pi would kind of get us out here. And so it's almost an exact replica of part B. We're just looking at a different little section of the graph. It's going to be the same exact answer there, an area of 0. And then from 0 to pi of the function 2 plus sine over x, well, remember that that is going to take this overall sine function and shift it up 2. So I'm going to attempt to draw the picture of this right now. Okay, so I took that entire picture up above right here and just kind of shifted it up 2 units. So instead of starting at 0, it's going to start at 2, going to go up 1, and then eventually fall 2, go up 2. And we're just interested in the area from 0 to pi. So I just want to point out that we have a rectangle right here that we can easily figure out. That area of that rectangle is, let's see, it's got a overall base length of the rectangle of pi and a height of 2, so that's the area of the rectangle. And then the area of this part is actually just the same as, well, it's what we started with right up here. Right, that is just 2. It's the same exact graph from 0 to pi of sine. That's basically what we're looking at in this little chunk right there. So add a 2 to it. And I really can't simplify that anymore. I guess I could say it's 2 pi plus 2, and that would be my best answer for letter E. So what should you take away from this video? When we talk about Riemann sums and fitting as many rectangles as we can underneath to get the exact area, we're now just going to call that a definite integral. And we can use definite integrals to find area under a curve. We generally think of that area as positive, but there are certainly times where functions go underneath the x-axis and then we just make that area negative. Most of the time in this section you just get to use geometry to do that. There is a way to do this through algebra, and when we get into tougher examples where geometry doesn't really help us out or give us that area, we'll use those methods. So for now, just use geometry. That's probably what we'll focus on tomorrow. I will teach you how to use your calculator for this. And then when we get to section 4, we get to learn all the algebraic methods to do this. And because you guys are such experts on antiderivatives, when we get there, you actually won't be too tough. We're just going to prove why we can use antiderivatives to help us out here. So jot down any questions, and we will see you in class tomorrow.